Section 8.4, testing the difference between proportions. As we said in Unit 7, proportions basically gives us a relative viewing of something by basically percentages. We may not know what a number means, but we know a percentage if it's a lot or a little. So often we use proportions as to determine how significant something is relative to the entire group. As in Chapter 6, we have to make sure our number of samples times our success, which is our p hat, is greater than or equal to 5. And that goes when we're doing for both two different sets of samples. They'll all have to be greater than 5. And you see here the standardized test statistic is very similar to what we do in Chapter 6. And what we're looking at here is basically finding the difference of the p hats, which is the sample p, divided by the square root of the population p and the population q, which is 1 minus p, times 1 over the number of samples for the first group and 1 over samples for the second group. And our p bar, which is population p, can be found by our samples of x1 plus x2 are successes over our total numbers, and our q's are 1 minus p. This isn't that hard, but let's go through this because this is several steps. A study of 200 randomly selected occupants in passenger cars and 200 randomly selected occupants in pickup trucks show that 91% of occupants in passenger cars and 83.2% of occupants in pickup trucks wear seatbelts. So it's a percent, so I know it's a proportion. And alpha equals 0.10. Can you reject the claim that the proportion of occupants who wear seatbelts is the same for passenger cars as it is in trucks? So the claim is, are they the same? Same meaning equal, meaning it's two-tailed. So our null hypothesis is proportion of 1, which is passenger cars, is the same as proportion of 2. If it is two-tailed and the equality statement is on the null hypothesis, the alternate hypothesis, P1 is not equal to P2. First, let's find our population P. This P line, as I showed before, is the population P. We may not have a true population, but it's actually pretty easy to find. We studied 200 randomly selected occupants in passenger cars and 250 occupants in pickup trucks. So this is our N1 or N2, basically for our population, 200 plus 250, which equals 450. And then what we did is we wanted to find 91% for the 200, 0.910. And if you multiply 200 times 0.91, you get 182. So that's our X1 right here. Then our X2 is 0.832 of 250, which is 208. So our samples here are 182 plus 208, which is 390, divided by the 450 for the population, which is 0.8667. That's our P bar, our population P. If our P bar is 0.8667, our Q bar, our failure rate, is 1 minus my P bar, 1 minus 0.8667, which is 0.1333. Now let's find the z-score. Well, as before, instead of the mu, we got proportions here. We assume my P1 and P2 for the total population is 0. So we look at the sample P, that P hat. P hat of 1 is 0.910, is up here. P hat of 2 is 0.832. So 0.910 minus 0.832 gives me 0.078. And then I have to divide that by the population sample deviation. And that is P bar times Q bar times 1 over N1 plus 1 over N2. Our P bar, we figured out up here for the population, is 0.8667. That's right here. Our Q bar, which is 1 minus 0.8667, is 0.1333. And then our 1 over N1, there's 200 up here for N1, number of samples for the first one, and 250 for the second one. So here it is, 0.8667 times 0.1333 times 1 over 200 plus 1 over 250. That ends up being, when I multiply this all out, 0.1159, which is 0.8667 times 0.1333, times 1 over 200 plus 1 over 250, a very small number, 0.009. When I multiply 0.1155 times 0.009, I get 0.001. So it's 0.078 over 0.001. The square root of that is 0.322. 0.078 over 0.322 is 2.42. So that is our Z. And as I put up here, 2.42 is my Z. It's right here. Now let's see what our critical points are. We said it's two-tailed. And 0.01 for two-tailed, which is 0.05 on both sides. And so it'd be 0.04. Let's see, 0.01 is 0.045 on both sides, because 0.9 in the middle. 0.45. That leaves 0.05 on both sides, which is 0.10. So from here to here is 0.5 plus 0.45 is 0.95. And 0.95 is 1.645, one of our common ones. So it's going to be negative 1.645 and positive 1.645. And I brought the negative Z table here. And this is 0.45 here, then this is 0.05 here. Let's see what 0.05 is. And that is right here. It's right between these two. 0.0505, 0.0495. So it's negative 1.645. And it's symmetrical and two-tailed, so it'll be negative 1.645 and positive 1.645. Which means my Z at 2.42 is in the rejection region. It's outside positive 1.645. These are my rejection regions here. So not only can I not support the claim, I have to reject the null hypothesis, which means they are not equal. Here's another one. This is a little interesting. These are yoga users. And we've got 3 different tables. We're going to use only one section of it here. They looked at the number of, there were 1,593 yoga users versus non-yoga users, 29,948. And this is where proportions are important. The yoga users are much higher percentage, much lower numbers than non-yoga users. But we're going to compare them by their percentage of yoga users. So I got 3 categories, age 40 to 49. There's 367 of those, which is 159 out of 1.953 is 2.2304. Income 20 to 34,999, that's 239 out of 1,593, which is 0.1500. Non-smoking 1,323 out of 1,593, which is 0.8305. And these are not unique. That's why this adds up more than 100%. We're looking at different characteristics. What we want to compare is the non-yoga users, 40 to 49, 6,290 out of 29,948, which is 0.21. And really what we're going to be doing is we're comparing this group to that group. For income, this group to that group. And non-smoking, this group to that group. So they ask you at alpha 0.05, can you support the claim there's a difference between the proportion of yoga users who are 40 to 49 versus non-yoga users who are 40 to 49? So we're looking at this group of 40 to 49-year-olds. And they say, support the claim there's a difference. Difference means it's equal or not equal. So we're looking at a difference here. That's on the alternate hypothesis that they're not equal, which means the null hypothesis is that the proportions are statistically the same. Let's find our population first. Our population of yoga users who are 40 to 49 is 367. Non-yoga users is 6290. That's right there. And that when I add those two up, that's 6657. And then of all the samples, number of people sampled, it's 1593 for total yoga users and 29948 for non-yoga users. So that ends up being 6657 over 541, which is 0.211. That's my population proportion for success, which means my Q line is Q bar, excuse me, is 1 minus P bar, which is 1 minus 0.211, which is 0.789. Now it's a plug and chug. And remember, this is 0. We're going to subtract our sample P of the first one, 0.2304 minus 0.210 of the second one. That gives me, when I subtract those, and remember the P1, P2 end up being 0, I get 0.0204. And that's all the way across here. Then my denominator for my deviation for proportions, it's my P bar times my Q bar, which is 0.211 times 0.789, times 1 over the yoga users, which is 1593, plus 1 over 29948 non-yoga users. Very, very tiny numbers. 0.211 times 0.789 is 0.1665. 1 over 1593 plus 1 over 29948 ends up being 0.00066. Multiply all that out, get 0.00011. The square root of that is 0.0105. So 0.0204 over 0.0105 is 1.94. And when I put it on the bell curve here, I got 1.94. They want to 0.05. And 0.05 means it's 0.95 in the middle here, which means it's 0.475 on both sides. So we're going down the middle, 0.475. And if I go 0.5 plus 0.475 is 0.9750, which I know is 1.96. But I got the negative z table, and remember, it's 0.025 on each side. So from the edge to that point. So if I look up 0.025 on the negative side, it's still, there it is, 0.0250, which is negative 1.96. And that's where it comes. And remember, it's symmetrical, so it's going to be negative and positive 1.96. And since that falls barely, z is 1.94, that falls in the fail to reject, which means we cannot support the claim, but the population of 44 non-yoga or yoga users versus the 44 non-yoga or non-yoga users are not statistically different. A medical research team conducted a study to test the effects of cholesterol-lowering medication, probably something like Lipitor or Crestor. At the end of the study, research found that 4,700 rank selected subjects took the medication. 301 died of heart disease. Of the 4,300 who took a placebo, 357 died of heart disease. This is a pretty realistic one because people may die during studies, and whether it's due to the drug or not, this is one of the first things they do. If the death rate among both groups, the placebo group as well as the drug group, is statistically the same, then they know they really can't look at the drug. Alpha 0.01 can support the claim that death rate due to heart disease is lower for those who took the medication over those who took the placebo. So they want to know, is the death rate lower? And that's the claim. And if it's lower, it's less than. So P1 is less than 3.2. It's left-tailed. The arrow's pointing to the left here, which means the null has to be P1 is greater than or equal to P2. I've got my numbers here. 300. I gotta find my P bar, my population P. 301 died who were taking the drug. 357 died who were taking the placebo. And then that's over 4,700 plus 4,300 for the total size of the groups. 301 plus 357 is 668. Divide by 9,000 for the size groups. 668 over 9,000 0.0731. And then my Q is 1 minus 0.0731, which is 0.9629. Find our P1 and P2. They don't give it to us, but we can figure it out pretty quickly. 301, which is the number of people that died out of the first group out of 4,700, is 0.064. My P hat for the second group is 357 out of 4,300. 357 died out of 4,300 who took the placebo. Is at 0.083. And now we're just going to put this in right here. Again, this becomes 0.064 minus 0.083. That ends up being negative 0.019. And then I multiply my P bar times my Q bar, 0.0731 times 0.9269 over 1 over the number of sample size, the first one, 1 over 47 plus 1 over 4,300. 0.0731 plus times 0.9269 is 0.0678. 1 over 4,700 plus 1 over 4,300 is 0.000445. When I multiply those together, I get 0.00002627. Square root of that is 0.00549. Negative 0.019 over 0.00549 is negative 3.46. So that's our z-score. And I put that right here. Now our z critical is 0.01. 0.01. We're going to do the negative side here, which means it's one-tailed, which means 0.01 is 99% right here. And that is 1% right here, which or 0.01. Now I look up 0.01 on the negative side, 0.0100. The closest I get is right here, 0.0099. That is the closest it gets to 0.0100, because this is 2 away, and this is only 1 away. On 0.0096, that's 4 away, 4 10,000ths. So we're going to go 2.33 here. Right there. Right there. So negative 3.46 is less than negative 2.33, which means not only do we reject null hypothesis, we support the claim that the death rate is lower for the people taking the drug than the placebo. So this is good for the medical company. Let's look at the yoga users again. This time, we are going to look at the number of people between ages who make incomes between 20,000 and 34,999. Support the claim of yoga users who use incomes is less than. So less than means it's going to be the alternate hypothesis. And it's pointing towards the left. So it's a left. One tail is left-tailed right here. Which means the null has to be greater than or equal to right here. So P1 is greater than or equal to P2. Let's find our populations. And again, they don't give us our population P and Q, or P bar or Q bar. But it's easy to figure out. Number of successes, which is 239 plus 5990 equals 6229. The total population is 1593 plus 29948, which is, as before, 31541. 6229 divided by 31541 is 0.1975, which means that's our P bar, which means our Q bar is 1 minus 0.1975, which is 0.8025. And now we plug and chug. This becomes 0. Our differences for each one of them, and we have to figure that out. It's right here. My proportion for P1, a P hat of the first one, is 0.1500, minus the P hat of the second one is 0.2000. That ends up being negative 0.0500. So that's my numerator. My denominator is P bar times Q bar, which we figured out, 0.1975, 0.8025, ends up being 0.1585. And then times 1 over 1593 plus 1 over 29948, which is 0.00066. We did this previously. When I multiply these out, I get 0.00011, and we did before. Square root of that is 0.0102. Negative 0.0500 over 0.0102 is negative 4.88. Negative 4.88 is right here. And we are looking at a 5% rejection one-tailed. And 5% rejection means that 95% is right here. All the way from here, which means this is 0.5 or 5%. And if you remember before, I didn't put the bar here. That's one of those ones that's negative 1.645 because it's not exact. It's negative 0.0495, or just 0.0495, and then 0.0505. And to get between that, it'd be negative 1.645. So that's our make or break, negative 1.645. My z, anything less than that, we would reject the null hypothesis, and it's way below this, negative 4.88. So we would reject the null hypothesis, and we actually support the claim that the incomes of yoga users between, or the number of income level of yoga users, number of people there by proportion, is less than non-yoga users.